Hello, type your registration numbers. So in last class, we started this discussion of non-parametric techniques where we assume no kind of distribution or standard shape for the probability density function. So we do not assume any kind of such shape for the distribution, but we try to estimate the density function. So we have gone through this slides where the basics of parzen window and k nearest neighbor estimation were discussed in brief. I think this point was not covered. So the initial way of doing this you can see as the histogram approach, where we can say if this is a 1D case and this is your x, that is variable, then you can have this probability on say y-axis. Then you can make small bins, say like this, of this axis, and then you can count how many samples do fall here, how many samples do fall here, and so on. Okay, so this estimation can be probability of x equal to k by n, where k is number of bins, samples falling in a bin. If this is a bin, then k number of samples are falling in that out of n, that is total number of samples, divided by v, that is the volume, so that it becomes density. So k by n by v will be my probability density estimation. Now you can do this thing, it's very simple, and there is a thumb rule of doing this. Say for example, if I have 100 samples in total, then bin size, number of bins must be at least 10. Okay, so square root of n is the rule to decide number of bins. If there are 100 samples, you will have 10 bins. Okay, then you can divide this scale in say equal sections with say 10 bins. So if this is my scale of x, then I will divide this, okay, like this, in 10 equal bins, provided I have n equal to 100. Now if suppose n is equal to say 400, then you will go for square root of 400. Okay, so maybe 20 bins. So like that we can do this. But if it is two-dimensional case, then instead of this kind of bin on x-axis, we have to have two axes, say like this. So this will be your x1 then, and this will be your x2. Then you have to divide x1 and x2 like this, and then you have to make bins. So this will be say one bin, and then you have to count how many samples say do fall in this out of n divided by its volume or area in this case. If it is 3D, then you can imagine it will be a volume. Okay, maybe like this. Okay, so like that we can proceed. So if x is d-dimensional, then number of bins is d plus 1th root of n. Say if my dimension is 9, then 9 plus 1 is 10. So 10 root n are number of bins you should make. Okay, so you can imagine that when it becomes multi-dimensional, this approach is very tedious to do, manually you cannot observe more than say 3 dimensions, then it is very cumbersome to implement this histogram approach. Okay, so that was the difficulty in using this simple approach that we have seen in a problem in very early classes. So this is my probability of say x given omega 1, and this was the probability function x given omega 2, and from that using Bayes we have we have found out the posterior probability of omega 1 given x, and this was probability omega 2 given x. So this was covered in earlier classes. You may go to the previous slide or lectures and just check this thing. Very early classes. Okay, so this was the approach of histogram. Now, to simplify our life, we need some other way of doing this. So this is, as you can see, this is a tedious way of doing this. How to divide such a scale, say for 1 dimension it's easy, maybe 2 dimension when it is more than 3 it's difficult, and there may be a situation if you have small number of data points, many of these bins are empty. You have made the bins but no sample is falling into that, so it will be empty. Okay, so such kind of problems you may face. So to tackle this, then we have this density estimation techniques that we have seen as introduction in last class. So here we do not assume any kind of underlying structure of the probability density function. We directly estimate its value. So you can have any non-regular shapes as your probability density function like this. These things are possible with this technique. Now there are two ways, as we have seen broadly, that we estimate density function for the likelihood. So this is my likelihood. I am estimating the density function for x in all the classes. So this will be probability density function of x given omega 1, omega 2, omega 3. So how many classes I have to find out, or I have to estimate my value of probability density function in all those classes. Okay, so here what we do, we, as you know, this Bayes rule. So here, this is my likelihood. So that we use, say, parzen window kind of technique to estimate this value, and this is prior and this is evidence, so this is known to us. Then we can do this calculation of posterior and take decision. Okay, so the procedure remains same for the decision making, but estimation of this quantity will be dealt by the new method, that is parzen window. Okay, so the thing is that you will estimate the probability density function by counting how many samples do fall in your bin divided by number of samples divided by volume of that bin. As we have seen this here, one example, suppose I am standing here, I want to find out the probability density function at this point, then I take a window Hello. सर क्लास है मैं कॉल करता हूँ. So I take this sample which is x of our interest and then count how many samples do fall here in this particular window divided by n, then volume of this particular window. So that is the way of doing it. And we have seen some theoretical constraints to implement this. So let us jump to actual method called as parzen window method. We will take one example so that this concept are more clear to you. Now parzen window approach estimates the densities assuming that the region Rn is a d-dimensional hypercube. Okay. Now here we will say define Vn, that is volume of the hypercube, equal to h to the power d. So h stands for the width of the hypercube. Say if this is my hypercube, then this is height or h, this is h, and this is also h. So if this is 3 dimension, then volume of this, that is V, is equal to h to the power 3. So we call it as Vn, it is equal to h to the power 3. Suppose this is a 10 dimensional hypercube, then volume of that will be h to the power 10. Okay, so basic thing is this will be my bin. Okay, so instead of dividing the whole scale of our interest into number of bins, what we are now doing is we are taking only one bin. Now there is a change. Instead of dividing the scale into number of bins, we take only now one bin like this. This is my bin. Now what we are going to do is we are going to center this bin around the point of interest. So suppose I want to find out this probability at the point x. Okay, this is my point of interest. So this x we will keep here at the center of this box, and we will have a hypercube of dimension h. Okay, so height, width, and depth of this is h. This is centered. So the center point here is the point of interest, that is x. And what we are now going to do is we are going to count how many samples do fall out of the given n samples into this bin. Okay, so that will be, say, number of points are k. Okay, so knowing this k divided by n divided by volume of this, that will give me the estimation of probability. That is the simple technique. Instead of dividing the whole space and then counting how many samples do fall in a particular bin and then keeping that thing in record, and then you find out for a given point of interest where that point of interest fall in which bin and then tell the answer. So instead of that, we do simple thing. We take the point of interest, that is x, and put a bin around it and then see how many samples do fall into this. So this is a reverse way, some kind of reverse way. Now here we can form a function, a window function, say psi of u, where this function returns me 1, this returns me 1, when uj, that is say mod of this, is less than equal to half. So that means it will return you 1 whenever you are inside the window. So whenever you are inside the window, it will return you 1. Outside the window or outside this hyperbox, its output is 0. I repeat. So this function, window function SciU, you can visualize here. So this is my function. So this function is such that whenever this u value is less than half. Say, why I'm saying, because if this is the center point, say this is one half this side and half this side. So half this side and half, say, this side. So like this, I have centered this box, say here, and whenever you are within the box, so if I to suppose take this point is within the box, so this function should return me 1. Meaning is that this function is such that whenever you stand within the volume or bin, it will return you 1. Whenever you are outside the box, it will return you 0. Okay, so this is the basic window function. Now you can move this window function throughout the space by doing this adjustment. You can change the center position as you wish. As per your choice, you can move this and you can check whether the given point falls within this box or not. So time being, you can just remember that there is a function which is doing the job that a given test point, if it is inside the volume, it will return you 1, otherwise it will return you 0. Now why I want this, that you will come to know in next slides. Now thing is that I want to count how many samples out of the total number n samples fall in that box. Okay, concept I can just revise here. So if this is the x given to you, what you are going to do is you are going to fit a box around it like this, and then you just want to see how many samples out of n samples fall into this volume. Okay, so that will be k by n, and then if you divide it by its volume, it will be p of x. Now to do this, to count or to find out how many samples out of n, given n samples, how many of them do fall in this box, what we do is we run this function over all the samples which are available to us, that I can call training samples. Say I'm just doing the counting, so I will be using this summation function here. So you can see here I equal to 1 to n, it is running from I equal to 1 to n, and this psi function is doing the job of checking whether the xi, that is xith training sample, is falling in this box or not. So what is my target? Suppose this is x1, this is x2 up to xn. This is my list of training samples, and I have found this box in my space. This is my box around this sample x. Now I want to find out how many samples do fall into this box. So this box is now represented by a psi function, okay, which is x minus like this. Okay, so this is our psi function. So what I'm going to do is I'm going to take these samples one by one, say from I equal to 1 to n. So suppose I take this x1, I go to this box and check with using this function, psi function, whether you are inside this or not. If it is inside, then this function will return me 1. Okay, so my count is now incremented from 0. Initially what I have to do, kn equal to suppose 0, then now kn equal to 1. Okay, because first sample do false. Then I take second sample, I check again with this function, and it is saying this function is returning me 0. That means it is outside the box, so it will be plus 0. Then I take third, then I find out that it is returning me 1, so I will keep on doing this. At the end of the nth sample check, I will get a count k. Okay, or I can call it as kn. So this kn is number of samples that are falling in this box out of n samples divided by again volume. So that will be my simple procedure. Now this kn, I hope you have understood, is counting how many samples are falling in my box. Once I do that, I can find out this Pnx, that is probability of at x, by dividing volume and n. So that we have seen already. So this is the way of using parzen window. Now instead of this kind of a rectangular cube, this kind of a cubical structure, hypercube, we can use the Gaussian window as well. Okay, so we can use n-dimensional Gaussian window instead of this cubical structure. So here is one example where we have considered the true distribution as normal with variance 1. So this is just one example to show how parzen window works. So assume that we have a distribution which is really normal with variance 1, and we are using the Gaussian window here instead of rectangular. So we are using a Gaussian window, and we will find out the probability density estimation using the same equation or using same parzen method. Now here, if I have only one sample and h, that is the window width, is 1, then see what happens. Since my true distribution is 0, 1, that means it is centered at 0, centered at 0. Now if you take only one sample, say h is equal to 1, and you take n equal to 1, you can see that the estimation is not centered at 1. Okay, it is slightly you can say biased towards the available sample, because this estimation is based on a sample, suppose somewhere here. Okay, so this is the only sample given to you out of the available many samples. Say n is equal to 1 and h is equal to 1. Now suppose I shrink this window, you can see that this lobe is squeezed and again it is more concentrated at this point. Now if I again squeeze it, it will be just around that particular one sample. So this estimation is far away from the actual distribution. Since I am using only one sample, the estimation is not that correct. Now suppose instead of one sample I take 10 samples, and again I have different window widths, say h equal to 1, h is equal to 0.5 and h is equal to 0.1. You can see that for h is equal to 1 compared to the previous, this is a better estimation, but when you go to lower h values, you can see a lot of disturbance is coming here. Now if you still further increase n equal to 100, then a more better estimation is produced. With again small window size, you will get this noisy kind of estimation. Now theoretically, if I go with infinite samples of the normal distribution, and if I take any window width, in that case I get the perfect estimation, which is the original one. Okay, so what this discussion tells us, that choosing h is very important. Choosing proper value of h. In case of window based methods, choosing a width of window is very important. And second thing is, you should have number of samples as large as possible to have very good estimation. In case of parzen window, you should have large number of samples to have better estimation. Now this is the density estimation for two-dimensional case, where we have h, that is window size 2 here, window size 1 and window size 0.5. Now earlier example was 1D and this is a 2D example. Now here I have only n equal to 1 throughout this row, then n equal to 10 and n equal to, say, theoretically infinite. So you can see here these distortions clearly for small values of h, and number of samples are less. Now in this case, we have taken intentionally two distributions mixed together, and then we have formed another distribution. Say we have here a mixture of uniform distribution and a triangular distribution. This is mixed and this is my original distribution. Now out of this distribution, we are drawing independently samples. Say here I am taking only one sample, and if I estimate using h equal to 1, so this will be my estimation. Now note that this is not the true estimation. The true estimation, or the true estimation, actually true distribution I should say, is like this, where there is a triangle and there is a rectangle. Okay, suppose I have this thing. I should say here not uniform. Okay, apart it's fine. It's uniform, and so this is the uniform distribution here, and this is triangular. So these are mixed together, and we have this P of X. Now if I take one sample out of it and then estimate, then this will be my estimation. If I take 16 samples randomly, then this will be my estimation. If I take 256 samples, this will be my estimation. If I take infinite samples, then this matches to the original distribution. Now, if I take smaller values of window, you can see that there is a lot of distortion. Now what we have to do is we have to estimate for a given test point the densities for each category, and then we have to find out the posterior of it and decide the class. Now we will straight away jump to this example so that things will be more clear. Now you may note down this example. This example is not available in book, so you can note down this. So here the question is estimate P of X if X is equal to 3.1 using parzen window estimate. Assume H is equal to 1. So this is given to us, and question is what is P of X. Now P of X is here 3.1. Okay, and H is 1. And this is your data, given data. Based on this, you have to find out the probability density function at X equal to 3.1. Only data is with you. Now what we do, given this thing, we first of all find out the window range. Okay, H is given to us. So what we do is we take the width equal to 1. So as we are centering the things around 3.1, so this is 1D data. Okay, this is 1D data. So we are centering the things around 3.1. So we will go this side 0.5 and this side 0.5, so that the total width is 1. So 3.1 minus 0.5 to 3.1 plus 0.5 is my range of this box, or range of this window. So it will be 2.6 to 3.6. It is looking like this, right? Now what is next step is to count how many samples from given list do fall into this window. So I have marked here red things. So this is 1, 2, 3, 4, 5 and 6. So these are 6 samples. They fall in the range 2.6 to 3.6. Okay, so I can see the window here and just check from minimum to maximum of this window how many samples from this list do fall into this window. So there are 6 samples. They are in the list. They are in the list and are falling in the given range. So K is equal to now 6. There are 20 samples. You can just count how many are there. Say 1, 2, 3, 4, 5, 6 and so on. So if you see, N here is 20. The volume is 1 here, since I have only H equal to 1, that too it is 1 dimension. So 1 to the power 1 is equal to 1. Okay, so P of X, that is density estimation here, is 6, that is k divided by 20 divided by 1, so this 0.3. Okay, so in this way we estimate the probability density at x equal to 3.1. So this is actually at 3.1. Okay, so this is a simple thing. I hope you understand the procedure. Just once again what I have done. So this was given to you. So this is the list which is given to you. This is my data. Okay. Then H is given to me. That is 1. So 3.1, H is 1. Then you take a range around this 3.1. So 3.1 minus 0.5 and 3.1 plus 0.5. Suppose I give you another problem, or you can take this as homework. Say homework. Now suppose I make H is equal to 0.5. What will be change? What will be change in my answer? So now this is my 3.1. I am centering this window here. So what will be max point now? So it will be 3.1 plus 0.25. And here it will be 3.1 minus 0.25. Okay, that will be your range. Then you have to, what is next step? Next step is to count how many samples from your list do fall into this window. Okay, so go to the list, and so this is actually manual implementation of that SIU function. Okay, what this function is doing, it is just checking whether you are inside or outside the given box. So what I am doing here, I am just checking how many samples from this list are falling in this zone 2.6 to 3.6. So that will be my value k. Okay, so here it is 6. Now you can see if I squeeze this, or if I make this h is equal to 0.5, then number of samples are obviously going to reduce, but volume is also reducing. So instead of h is equal to 1, now h is equal to 0.5. So this p will be now 0.5. So you have to divide by 0.5 in that case. Okay. Now let us use this parzen window in second problem. So problem is, we can also note down this problem. Here the problem is classify X test is equal to 3.5. So you have to find out the class for this if, say, this is omega 1 and this is omega 2. So these are the samples of omega 1 and these are the samples of omega 2. And here the count for omega 1 sample is 20 and the count for omega 2 samples is 11. Okay. So this is same from the previous problem. Only thing is that I am giving you list of omega 2. And what is task? Task is to classify X test 3.1 using parzen window method. Now from previous problem, we know that this probability of X is equal to 3.1 given omega 1 is 0.3. So that we have calculated in last problem. Now here we will calculate for the omega 2. Now what we have to do is, again we need h, so I'm taking h equal to 1 in this case. So the range is same as previous problem. So in previous problem range was 2.6 to 3.6. So 2.6 to 3.6 is my range. In this range from omega 1 there are, I think, 6 samples that we have seen in last uh, problem. Now here in this range you can mark out how many are there. So 2.6. So this is there, this will be there, up to this will be there. I think 3 are there. Okay. So you can just take into account the proper numbers. So this will be, I think, 3 by 11. Okay, this will be 3 by 11 for omega 2. Now we can calculate the posterior using base. So this is the...
Sir, why are you calculating 2.1?
Why are?
Why are you considering 2.
Repeat your...
2.1 is out.
Sorry, yes.
Hello?
Yes. You are right. So we are from 2.6 to 3.6, right? So I think this will be 2. So this is correct. So this is correct. You are correct. Okay, so this will be 2 by 11. Then use this likelihood estimates. So these are our estimates. You substitute in your base equation, say here for omega 1, and you will get the estimates, you will get the posterior. So this will be 3 by 10, 20 by 31 divided by P of x. So I am not calculating this P of x, which is not required for taking my decision. Now what is this 20 by 31? So this is the prior knowledge, because there are 20 plus 11, total 31 samples. Out of 31, there are 20 samples for omega 1. So I'm just taking this as 20 by 31 as my prior. So this is likelihood, this is prior divided by P of x. Okay, so it will be, I think, 6 by 31. Similarly, we can calculate posterior for class 2. So this is 2 by 11. So this was rightly pointed out as 2 by 11, and then 11 by 31. So why 11 by 31? So there are 11 samples in omega 2 divided by total number of samples. So that I have done, and this P of x is as it is. So 6 by 31 and 2 by 31. So which one is big one? So we are using base, so we will go with maximum probability. So obviously my answer is class. So I should declare this as class 1, or X test belongs to class 1. That is my answer. So if you have any doubt, you can ask. We will see the parallel implementation of this parzen window method called as probabilistic neural network, or it is popular as PNN, tomorrow. Okay, if you have any doubt, you can ask or you can stop.